So robot dynamic model, we'll see how to, what it is and how to derive it. A bit of background, we're gonna talk in general about dynamics, because until now we talked only about kinematics. We'll talk about a quantity called the Lagrangian, which is very convenient and so on. We'll talk about potential and kinetic energy, inertia, moments of inertia, and how this all apply to a dynamic model of a robot arm. At any moment you have a question, I'll go quickly today because we have more topics to more ground to cover, but at any moment you have a question, don't hesitate, just raise your hand. I might be going a bit too fast. So what we did so far, forward kinematics, it's basically this 4x4 matrix, rotation and translation. Jacobian, how we go from joint velocities to end effector velocities, and we'll see that we're going to need these two concepts today to define the dynamic model. All right, so we basically defined a way to calculate inverse kinematics and velocities, and how can we use this to calculate the trajectories last week. So we did basically big part of the modeling, and today we're combining them for the dynamics. It's basically what we did so far is all kinematics, and we're going to start talking about dynamics. Anyone knows the difference? This is also called kinetics sometimes. What is missing from our discussion so far? Forces, right? Dynamics is about forces, and so kinematics is about motion, but just describing geometrically, like, okay, where things are, coordinates and so on. While dynamics is about what causes this motion, right? Right, yes. Because in order to have motion, we need to have forces or torques, as we'll see today. Great. So what we're trying to define is basically equations of motion for the robot, which means, as probably you know from the past from physics, equations of motions are differential equations. They have to do with velocities, accelerations, and these are derivatives of position. So we're talking about differential equations that gives the relationship between input forces or torques and resulting joint accelerations, or whether they're angular or linear. Angular for revolute, linear for prismatic. Why would this be useful when we're trying to develop and design and control robots? Where do we need this kind of differential equations? All right. So where did you encounter differential equations? In state space, you said? Yeah. Right. Yes, where you used it to basically control a process, right? So it's about control. It's about basically predicting how would the model behave under different inputs in the end, right? That's why we need the relation between inputs and, acceleration or behavior over time. So we need this for controlling. We need to have a model for this behavior so we can actually control it. Because what we're actually controlling, again, it's the joint positions and velocities, yes, but really the down level is the forces that the joints produce, the torques and the forces of our prismatic joints that they produce to actually move the robot. All right. Do we know any equation that basically gives us this relationship?
Force equals mass times acceleration.
A bit more correct, sum of forces. Right, okay. Being academic. Very famous equation. Basically this is telling me the same thing. Like, okay, for a given force, what will be my second derivative for position or acceleration? Which is obviously developed by Pythagoras, Newton, in the 1600s. Not everything comes from the Greek. All right. However, this kind of formulation is a little bit stiff for this kind of application. If we try to model, basically, if we try to use Newton's equation to model the robot, we need to take each part of the robot, its link basically as a separate body, calculate all the forces that act on the body. That's why we have sum of forces, and calculate its accelerations. But these bodies are basically constrained relative to each other, and that's a bit complicated to model using Newton's second law of physics. Right? I'm not going too much into detail, but you can think that, okay, we have to calculate basically all the reaction forces that happen at the beginning and the end of each link, and that's not straightforward. It's possible, but it's just not convenient. So Newton put this, foundation with these equations, but a couple of 100 years later, some other guys, namely Lagrange and Euler, they found a different way to formulate Newton's three laws for motion, and they produced a more general description of nature in a way that can give us the same resulting equations of motion for the same systems, but starting from a different point. So basically, Lagrange realized there is a fundamental property of a system called, he didn't call it himself Lagrangian, but now we name it in his honor, a Lagrangian, which is basically the difference between the kinetic and the potential energy of a system. Right? Now we call this the Lagrangian of the system, and this is basically giving us a lot of information about how the system will evolve over time. Right. It's the principle of least action. I'm not going into all the details, but if you want to research more, that's how you will be able to find it. Right. So here we have this Lagrangian, and I write here as a function of Q and Q dot. Basically, Q and Q dot are what we call the generalized coordinates of the system, or you can think of it in terms of state space. It's basically the states of the system. Another way to describe it. It's the other way around. The states that we use for a system is the generalized coordinates, but basically a state of the system is everything we need to know about a system in order to predict how it will evolve. And we typically, the states is the positions and the velocities of the system, or the states and the derivatives of the states for a system, right? Good. If we have defined this quantity for any system, right, regardless of robots, we can describe the evolution of the system over time under given inputs by deriving this Lagrangian with the derivatives of the states, the derivative part of the states and time. Basically, we have this complicated looking derivation that we will break down, and you'll see that it's not that complicated. We have the Lagrangian, the partial derivative with the derivatives, and that over time, minus the partial derivative of the Lagrangian with the states, and that is equal to the inputs. In the simplest case, we have just one variable here, q. Let's say one thing that evolves over the system, that describes the system and the velocity of that, or the differential over time of that quantity, and then we have one input. But as we see for robots, then these can be vectors, so we can have multiple inputs and multiple Q's and so on. Right. So we say the Lagrangian is kinetic minus potential. Do these terms sound familiar? You heard about kinetic energy, potential energy in the past? Potentially. Right. So, what is potential energy? You didn't see what was there. How would you describe potential energy of a system or of a body or whatnot?
Kind of like energy latent, or like it is contained into an object.
All right.
Either by mass or by
So it's stored energy, as we say, contained. It's energy that we store in a system, right? And it has the potential of being.
Usually consists have potential energy like gravitational or elastic.
All right, yes. So, in the interest of time, yes, energy possessed by an object, and it can be either due to gravity, so basically due to position of the object with respect to a gravitational field or an electric field. It can be due to stresses within itself, like basically elastic compression. This creates stresses within the object, or electric charge, or other factors, right? But it's energy contained in the system, and it has the potential of being, released. That's why it's called potential. So you mentioned some sources of potential. Gravity is one. You said springs, so elasticity. Other sources of potential. Sorry?
I said mass, but it is related to gravity.
Electricity, gravitational fields, electrical field. This is also a field, right? I wrote gravity. Other sources. This gives us already a good list, right? And the effect of these fields on robotics, they have different, different contribution, right? So in general, for the types of robots that we will talk about, we neglect any elastic deformation. So we assume the objects are rigid, so we don't have any, energy stored due to deformation. That's an assumption, but depends on the robot that we're using. It might be a very good assumption. If we have flexible robotics, for instance, it's not a good assumption because things deform. But if we have rigid robot arms, then it's good enough. And we also assume that they are electrically neutral, so there is no charges between the objects and the world. That's a much better assumption than the elastic, because if these would be electrically charged, it would be dangerous. So we typically ignore these sources of potential for robotics, but gravity is an important one. So we do consider this important, because basically we have this robot has masses that move in the gravitational field, and based on their positions, they will have an effect on the potential energy of the system. Like this robot will have, I don't know, different potential in this configuration than, I don't know, in this configuration, whatever. And we'll see what is the potential due to gravity. All right. So the most common source of potential energy for robotics is the gravitational field of the Earth. Unless we're doing, I don't know, Mars robotics, then it would be gravitational field of the Mars. Anyone remembers how do we calculate the potential? What is the formula? mg_h. Right, mg_h, correct. So V is the typical letter we use for potential energy. And indeed, for gravity, it would be mg_h, where m is the mass of the object, j is the gravitational acceleration, and h is the height of the object, right? But height from where? Now, when I say mg_h for, let's say, this piece of chalk, what height am I talking about? Sorry? We need to have a reference point. Also, what should be a proper reference? The ground. The table, whatever. It doesn't matter, because what we care, basically, the same way, where else do we encounter potential? The concept of potential in electricity. We have voltage, but voltage is basically what we're measuring. It's never like, voltage on one wire. we always measure voltage difference, right? So we always have like a, potential as an absolute measurement doesn't make a lot of sense. We always take about the difference of potential, right? And then basically what we see is that for the difference of potential, the reference doesn't matter. So we can have, let's say, an object with some height measured from the ground or measured from another height. So these theoretically would have a different absolute potential because the height is different, the same object, right? But if I'm talking about the difference of potential between, this position and this position of the object, the delta has, it's the same difference regardless of the reference. So yes, we should have a reference to calculate all the potentials that we'll calculate today, but in the end we'll see that it doesn't matter so much. It doesn't matter at all basically, because what we will end up using is the difference of potential, which is the difference of potential will be basically the difference of the height, as long as we don't have mass differences. And the reference doesn't matter anymore. However, keep it as a rule that, okay, we always take the same reference for all the potential calculations, just so we have the same thing. All right, so potential, let's write it here, mg has. What about kinetic energy? What is kinetic energy?
Mass times velocity is the energy based on the movement of t.
All right. So potential is the energy stored in the system and it can be, given out, while kinetic energy is energy due to the movement of the object, due to its motion. Right. And that's it. What influences the kinetic energy of an object? So we figure out the equation.
Mass and velocity.
The mass, so how heavy it is or how massive it is, and how fast it's moving, right? And we're basically discussing about two types of kinetic energy. It's the same thing, but yeah, we split it for convenience. We talk about linear and angular kinetic energy. You remember we talked about linear angular motion and velocities on the Jacobian lecture for any part of the robot. Since we have linear and angular velocity and we say that the kinetic energy is affected by velocity, then it makes sense to also separate kinetic energy to linear and angular kinetic energy, right? So, the linear kinetic energy would be with how fast the object is translating, and the angular will be with how fast it's rotating. All right? Now we go to the equation. So what would be the form for the angular linear velocity? What do you remember?
M times v squared.
M times v squared over 2. Right? So that's correct. Now, I write it a bit weirdly here, whatever. So instead of writing u square, I basically put it this, like this, because what you said is correct, but that is for when velocity is a scalar, right? And I want to use vectors. And you'll see later on why. So if I use vectors, I cannot do the square of a vector, because that's 3 by 1 times another 3 by 1. I cannot do that, right? So how I calculate basically the square of this is by transposing one of them. So this will become 1 over 3 transpose, so that I have basically a scalar. Why a scalar? Because the mass is a scalar, okay.
Because the energy is at the vector.
the energy is not a vector, right? The energy doesn't have any direction. It's a property possessed by the moving object, and the energy doesn't, it's not a vector, it's a scalar, right? So we need this to become a scalar, right? I mean, yes, all right. So if I transpose this, basically, what will I have? I will have ux, uy, uz, and here I will have ux, uy, uz. So if I do this multiplication, I will have ux square plus uy square plus uz square. So this will be basically the norm of the velocity vector, so similar to the u square, right? So, right. So this one with the norm of the vector square will be equal, right? Because the norm of this vector is square root of ux square, uy square, uz square. Square, then the square root goes away, so then this will be equal. All right. You will see later on why I need them in this form. All right. Any questions so far? Things should be straightforward. Right. What about angular velocity? So this is linear velocity, where I have, linear kinetic energy, which is calculated by mass and linear velocities. What about angular kinetic energy? How do I calculate the kinetic energy for something rotating?
You have to consider the rotational, the
angular velocity. So I will have some angular velocity here. Angular velocity is again a vector, as we saw. So again, I take this one. Right. It will be again 1 over 2. And I will need some kind of inertia.
angular.
Right. So we said that kinetic energy has to do with the mass, how massive an object is. The heavier the massier it is, the more energy it possesses for the same velocity, right? And the velocity, so how fast it translates. The same logic is here, like I have angular velocity, how fast something rotates, and then I need some kind of measure of inertia.
Angular momentum.
Moment of inertia?
Moments of inertia. They sound similar, but angular momentum is not the same thing as moments of inertia, but yeah, basically we have a quantity here, which we typically denote with I. It's not an identity matrix, but it gives me the equivalent of mass, but for rotations. I'll come back with slides on this, so it's a bit easier to explain. In the meantime, I have this basically equation, as I said, and that's it. And yes, the goal is to calculate the Lagrangian, which was v minus t. So I need the total t here, which will be basically the linear plus the angular kinetic energy combined, which will have this form. Now, what is this I? And I'll try you to explain to yourselves, like, what form do we have here. So for translation, let's say I have an object and it might move in different directions. The inertia is the same whether I'm moving that way, or that way. Or do I have different inertia when I'm moving this axis, or that axis? It's the same mass or not?
The mass is same.
It's the same mass, right? So then the inertia would be the same, right? No?
Inertia depends on axis of rotation.
No, translate. I'm just translating now. I'm not rotating. I'm just translating, right? So I just have a scalar basically called mass, which doesn't influence, on what direction I'm moving. I will have the same inertia. When I'm rotating, I'm trying to find something long, and I don't. Whatever. Usually have a broom here, but yeah, can imagine this is very long. Do I have the same inertia whether I'm rotating, in this direction, or in this direction? No, why not?
Because the angular velocity applied to that point, but I don't know, to the rotation of the object.
The mass is distributed differently along the axis of rotation.
Yeah. So here, I will have more inertia when I'm rotating like this, because the mass is further away from the axis of rotation, than if I'm rotating like this, where it's closer to the axis of rotation. So I will need more torque, basically, to rotate this, because the masses are further away, right? Great. So then here, I don't have a scalar anymore. Right? I don't have the same quantity regardless of where I'm rotating. Basically here what I can do is, move this away, because here I will calculate basically the norm of the velocity, a scalar, and then multiply it with another scalar to get a scalar. But here I cannot do this, because I have different inertias around different, axes of rotation. Right, so then what makes sense do I have here? If this is not a scalar, what does it have to be? So that in the end, the angular kinetic energy is still a scalar, because we said energy is a scalar, right? So this has to be a scalar. So what do I have to have here, if this is not a scalar, like m was? Like this I can do, right? Because it's scalar. But if this is not a 1 by 1, what does it have to do? So I can do the multiplication. A 3 by 3, right? So moments of inertia is a 3 by 3 tensor, call it, or matrix, or how you want to call it, which basically shows me for a given torque what will be the resulting acceleration. So here I have omega dot, so that's angular acceleration. So how am I mapping input torque to angular acceleration? Because if I have this weird distribution of mass, then in order to rotate around a certain axis of rotation, I shouldn't give a torque around that axis of rotation. It has to do with how the mass is distributed. Basically, we have these 9 numbers that make the moments of inertia, and how they're calculated. Very briefly, this is just for reference. You don't have to calculate moments of inercia, advanced topics, but just so you understand what does mass distribution mean. If I have a system of bodies, so basically discrete masses, like this Ixx, so this element here would be the sum of all the masses and the distances along the axis of x. So for Ixx would be the sum of all the masses and the distances along the around that axis x, which is basically y square plus z square. This would be, the distance around that axis. So if this is the axis of rotation and I have a mass here, and this is y and this is z, this will have some coordinates. This is yk, this is zk. If I take the square plus the square, I will have basically this distance, right, the radius. So the moment of inertia will be the sum of all the masses times their distance from the axis of rotation, right? For x, this will be the same for y. So the sum of all the masses and the distance along the axis of rotation y, z, and so on. So basically in this example, for yxx, for rotations around the x-axis, only these two masses will have distances, so only these two masses will affect the moments of inertia. For rotations around y, it will be these 3 masses, because basically m2 will have 0 distance from the axis of rotation. Basically x and z is 0 here. And for z it will be these 3 masses. And depending on the distances and which masses is bigger, then I have different basically numbers for these 3 values here. So these 3 values would show me what is the inertia of the system when I'm rotating around the x-axis, when I'm rotating around the y-axis and the z-axis. And I can calculate the other parts of the tensor. So Ixy is basically the sum with product of these two distances, of these two coordinates, and so on and so forth. And you see that basically I have this is a symmetric matrix. So Ixy is the same as Iyx, and the other way around. And this is used to calculate basically in this equation, you know, for any arbitrary rotation, what would be the resulting acceleration. This is in the case of discrete masses. If I have, for continuum bodies, let's say I have this link, then I basically take triple integrals for the, it's basically the same calculation, the same distances, but with a density, because density is basically the mass distribution on the continuously. Don't be scared by the triple integrals. You will only have to calculate them once for the exam. No, I'm kidding. This is not part of the exam. It's just, you know, to explain you what is the moments of inertia. Rather complicated to calculate. Right. For simple objects, we have analytical solutions or approximations. So basically, we typically model robot links as rods. So basically, very thin or, you know, almost infinitely thin bars of some length. And yeah, this one, we can assume we have this moment of inertia for this kind of bars. So we typically use such a formulation for links, right? We have to be careful with the axis, because here we assume the length of the bar is on the x-axis. And as we assume like an infinitely small radius for the bar, you see we have zero inertia when rotating around the x. But yeah, this is an approximation, but it's good enough. Usually it's good enough. All right, any questions? So that's what this I is. Good. So overall, Lagrangian kinetic minus, kinetic minus potential energy. Potential energy just due to gravity. mg has. Kinetic, we have to split to linear and angular. For linear, we need the mass and the velocities. For angular, we need these moments of inertia and the angular velocities. All right? Let's see a very simple example of how come this approach gives equations of motion with the derivation we saw. All right, so we have this very simple system where we have just one object moving up and down, so 1 degree of freedom. Doesn't move left and right, doesn't rotate, nothing, just moves up and down. And let's see if by calculating the Lagrangian and doing the derivation we said earlier, let me write this as well. So this is the derivation. Equals input, torque, but yeah, we'll see here. Before we start, what would we expect to be the Newton's solution? So for this system, we can calculate the equation of motion from Newton. What do we expect it to be? This thing moves up and down under gravity. It has some mass. I didn't put the mass there. Right. Sorry, what? So we have some force, external force, F, plus gravity.
Oh, so there is an external force?
Yes, yes.
Well, F plus the gravity?
F.
And minus the gravity depends on the...
And let's consider y pointing upwards. So then it would be minus F minus mg, right, the gravitational force, equals the mass.
And the acceleration.
Acceleration, since I'm moving on the y-axis, it would be y dot dot. Okay, that's what I'm expecting to be from Newton. Let's see if Euler-Lagrange gives me the same thing. So what would be the potential energy of this system?
Mass times
G.
m times h.
So for this one, it would be basically mj y, right? Just to keep the same coordinate. Linear kinetic energy. Come on. 1/2 velocity.
What's the derivative of y?
Derivative of y, really nice, squared. Or I can do, but since I only have one component here, it's the same thing. All right, angular velocity, angular kinetic energy, zero because it doesn't rotate. Great. So this means my Lagrangian is, I didn't write it very, I have to improve on my real estate when writing. So the Lagrangian will be 1/2 m y dot square minus mg y. And then I'm saying that if I do this derivation, I should end up with the input for my system, which would be the force. All right, so let's do this derivation. Let's start with this part first. Derivative with q dot, which in this case it would be my general coordinate will be y, right? Because that's the only thing that varies. Right, so derivative of the Lagrangian with y dot. So this one will be 2y dot, 2m, sorry, what? 2 times 1/2 my dot, right? So my dot. All right, and then this one I have to derive with time. So the derivative of this with time will be really nice. I knew I can do this lecture, these 2 lectures in 2 hours with you guys. Great. That assumes that mass doesn't change with time. Otherwise, I would have to calculate the derivative. But
So basically we had another derivative because of the time. No?
yes, because what's the derivative of this with time? It's the derivative of this with time times this, which the derivative of this with time is 0 because it doesn't change, plus this times the derivative of this. We add another dot. Clear for everyone? All right, so what is the derivative of L with here I put y, here I put q. The derivative of L with y? Minus mg, because this one doesn't depend on y. This one does, and y. So if I write these two together, I will have my dot dot minus plus mg equals force. And yeah, signs, well, I can put minus force here if I want to be correct. And then I basically end up with the same thing here, right? Minus F minus mg. Correct? It's written the other way around, but yeah. All right. Why I put a minus here, it depends what I consider positive force, right? The force, since it's an input, it can be pointing up, down. You know, when it's pointing up, I say it's positive. When it's pointing down, I say it's negative. So I actually, to be more correct, it should be like this. I think, more general. And then I can put negative values for F when it's pulling down, positive when it's pulling up. All right? Convinced you? Euler-Lagrange did it right? Yes. So the state of the system would be basically my coordinate and the derivative of the coordinate. We write the Lagrangian as we did on the board, and we do the derivation, differentiate, okay, and then eventually I have the same solution, same as Newton's second law. Now, to show you why this is convenient, a short example, what if I now allow rotation as well of the ball? What changes? And I'll erase here. Sorry? Yes, and also for the Euler-Lagrange we will have another input since we have another state, basically. Exactly, we will have angular velocity as well. Does this one change?
No.
As long as the mass of this ball is equally distributed and the center of mass doesn't change when I rotate the object, then it doesn't change. You know, if it would, then this would be a function of y and theta as well. So if the center of mass will not be in the center, but let's assume it is for now. All right. The linear angular velocity does not change, and the angular velocity, the angular kinetic energy, is now what?
So
Theta dot, because it's velocity, times moments of inertia, and times theta dot. It's not correct to say moments of inertia because basically this is not a vector. So I will have a fixed value for the let's say theta here. I will have a fixed value. So here I will have a scalar because I only have one possible rotation, right? If I want to take a tensor here with 3 by 3, then this should also be vectors. So I will have to describe this in 3 dimensions, even if they don't move in the other dimensions, but I will have to have vectors where basically I will have, I don't know, theta dot 0, 0, and theta dot 0, 0. And this would result basically eliminating all the elements from here. So only one element from here would be basically coming out, this theta. All right. Good. How do I deal with Euler-Lagrange now? My Lagrangian is a little bit more complex. So I have 1 over 2 m y dot square plus 1 over 2 theta dot square times I theta. Let's do it the same form. Inertia, angular velocity minus mj y. If I ask you about Newton, would you know how to describe that with Newton? Yeah, okay.
Well, we have again the gravity.
Okay, so mg and the force. And I will have again the same form for the linear part. And?
a sinus or something for the angle theta.
Would the linear acceleration be affected by this rotation? No, since the center of mass is in the middle, right? That's important.
But if it's like, I don't know, a huge line, it will affect, I guess, no? If it's not a ball, the object.
If it's not a what?
It's not a ball, the object. It will affect the rotation of theta.
If it was what?
I don't know, a bar of steel or something like that.
As long as the center of mass is in the center, it wouldn't affect it.
Yeah. But if it's on the one end of it's, I don't know, in the lower part of
The center of mass? Then it would affect. And we'll see why very, very quickly. Okay, so this is Newton for translation, for rotation. Sorry? Centripetal force. Yes.
Different inside the body.
Yes. You will basically have this thing. The torque that you apply on this rotation would be this moment of inertia times the acceleration around that angle. We saw it very briefly earlier. Yeah, you don't have these centripetal forces because that assumes like a mass rotating around with a radius, right? And here, that's why I keep on insisting that the center of mass is in the middle of the rotation, so there is no mass being rotated. But we still have inertia when rotating this, right? Because there is mass distributed, it's just that, you know, the center of mass in the middle. So we expect this from Newton. Let's do the derivation here. I basically now, because I have 2 degrees of freedom, I do 2 derivations. One with y, as before, and one with theta. Theta dot minus theta equals the torque. All right. Did anything change here? So, what depends on y dot and y is basically these parts, correct? So this new thing that we added does not depend on y and y dot, so all the derivatives here will be 0. So this will be still the same thing. It will be this one, correct? I'm not redoing it again. What about this one? Now these terms don't depend on theta and theta dot, correct? So I only take the derivative of this. What's the derivative of this with theta dot? I theta theta dot. This is 2 times here, these 2 gets cancelled, and the derivative with time will be theta dot dot, correct? And what's the derivative of the Lagrangian with theta? There is no theta here, so this will be 0, so this will be equal to tau. Right, same thing as here. Okay, very, very quickly, what if the mass was not in the center? What would have changed? This would have remained the same, but I would have a different, I would have some different potential based on the theta. So basically, let me try to draw this. Let's say I have this ball rotating, and the mass is here, the center of mass, right? What do we say is potential is the height of this mass, right? And the height of this mass depends on the rotation, right? When the ball rotates, this is higher or lower. So there would be some sinus of theta times this distance, sinus of theta, yes, times that distance, right? So here I will have this one plus mg, or wait a bit, no, it will be y plus, I don't know, this r sine theta. Okay, so then I would have something depending on theta here. Remember earlier I said there's no theta here, but now we'll have something on theta, and it's even like a nonlinear function, and you know, my equations of motions would get a bit different. Okay, you see that the more complex I make my system, the more difficult it is to predict what Newton would do, because now if I tell you what would Newton predict for this system that the mass is not in the center, but you know, when we model the potential and kinetic energy and use Euler-Lagrange, we can calculate things just by deriving. All right, any questions?